let's now just talk about one thing, which is called inductance before the break. Okay, so what's the notion of inductance? Let's say that you have two loops. So this is loop 1 and this is loop 2. And let's say that you have a certain current in the first loop, I1. So this will create some magnetic field coming out of the first one. And this magnetic field will induce a flux in the second one. So the flux in the second loop here can be written as the integral over the surface 2, dA2, of the field B1, which is created by loop 1. Okay? Therefore, if I have two loops and I drive a current through my first one, I generate a magnetic field. This magnetic field can be time dependent. But anyway, this magnetic field that's created creates a flux in the second loop. And if there's time dependence, I will be able to induce some electromotive force in the second loop. Okay, so we can just write a couple of equations like this. So because B1 is proportional to the current I1, we can write this relationship here as the flux in 2 is some number M21 I1, where this number is called the inductance. Okay, inductance here you should read as a word as the kind of propensity to induce into something, right? So the way it's able to do this. Okay, so just a couple of fun formulas for this. We can write this phi 2. Once again, just using Stokes' theorem. I'm just starting back from here. So what I'm doing here is indeed just using the fact that B is the curl of the first vector potential. So actually, I don't even need Stokes' theorem just yet. So it's the integral over S2 dA2 dotted into the curl of the A that is produced by the first loop. Okay, so now I can use Stokes here and turn this into an integral over the P2 path that I have here that defines my second loop of DL2 dotted into this A1. Okay, so that's just using simple identities. But I had that this A1 here, we had an integral for this from our earlier equations. So this A1 given at a certain vector R is equal to mu0 over 4 pi. So it's really like coming out of the Biot-Savart, and we wrote an integral representation for it. And I've got now an integral over the path P1 of the first loop, DL1, of the current I1 divided by R minus R1. Okay, that I'm integrating over now. So it's just the current over, and this is like the vector current that I have. So this is an earlier equation that we had. So what that means really is that if I look at the expression that I have for the inductance, then I've got the proportionality with I1. So this inductance here becomes a purely geometrical relationship between the two loops. Okay, so this this phi 2 is equal to mu0 I1 over 4 pi. And now I've got the integral over path P2 dL2 dotted into the integral over path P1 dL1 of just 1 over R2 minus R1. Okay, taking out the stuff from the integral. So, okay, so said otherwise, if we write it cleanly, M21 becomes a purely geometrical double integral over the paths. So P1 integral P2 of dL1 dotted into dL2 divided by R1 minus R2. This is not an equation that I want you to remember by heart. Just want to write it down to emphasize the fact that it's purely geometrical. Given path P1 and P2, you can compute this inductance here. Okay, and this is quite handy because now you can really tell me what happens in a second loop if I do something in my first loop, or conversely, what happens in the first loop if I do something with my second loop. Because manifestly, this relationship between the two loops is symmetrical. So manifestly, M21 is equal to M12. It's a symmetrical thing. Whatever the inductance is one for the other, it's the same the other way around. Okay, so that's just one little relationship here.